Hello, so today we will continue with our talk on X-ray diffraction and reciprocal lattice. So what we did last time was uh, more like speaking about reciprocal lattice and how we calculate reciprocal lattice vectors if we know the direct primitive lattice vectors, okay? Today, you will see why did we learn that and we will put it into use. So physicists study crystal structures using various forms of radiation, such as photons, electrons, and neutrons. In this chapter, we will learn that the information gathered from the scattered particles can be analyzed to learn about the crystal plane spacing, as well as the kind of atoms that compose the crystal system. What makes crystal diffraction different from ordinary light ray reflection or refraction theory is the wavelength used. If the wavelength associated with the radiation is large compared to the lattice constant, the result is simply standard reflection or refraction. When radiation wavelengths on the order of the crystal lattice constant undergo elastic scattering from the crystal atoms, diffraction occurs in directions quite different from ordinary reflection. To see how this happens, we will look at diffraction theory explained by Bragg's law. Just as waves propagate on the surface of water if we throw a stone into it, similar waves spherically propagate in all directions if we irradiate a crystal by X-rays. The spherical waves originating from different lattice points of the crystal superimpose and become enhanced or extinguished. This is referred to as interference. So what we are observing here are interference patterns. At some points, there is nothing, okay? You can see here these black spots, there is nothing. And at other points, there are these rings that are bright. So these are the interference patterns. It was found that at certain specific wavelengths and at certain specific incident angles, the crystals reflected radiation produced diffraction peaks, Bragg's peaks. Diffraction is an example of interference, whereas interference is the superimposition of only a few waves. Diffraction is the result of superimposition of a large number of waves. William Bragg imagined the crystal to be composed of parallel planes, spaced from each other by a distance d. The crystal acts as a three-dimensional grating, which causes diffraction peaks to occur wherever the crystal reflected waves interfere constructively. Thus, with d, the spacing between the planes, if lambda, that is the wavelength of the incident beam, is of the order of magnitude or less than d, that is small enough so as not to produce standard reflection and refraction in the crystal, we suppose that the incident beams are reflected by the atomic planes. The outgoing rays experience constructive interference if their path difference is a multiple of the beam's wavelength. Okay, what is the path difference? So here we have wave 1 and we have wave 2. This is here, wave 1. And this is wave 2. Okay, what is the path difference? So this is wave 1, this is wave 2. The path difference from this side is this distance over here. Okay, and when they get diffracted, this is also another distance. So we need to calculate this distance and multiply it by 2, and this will be the path difference. How much is that? Now look at this triangle. So this is the distance I'm interested in. I'm gonna call it X, okay? Now look at this triangle. Okay, This triangle is right over here. Okay, now this is theta, and this line is parallel to this line, so this is theta. So this angle over here is 90 minus theta, so this angle over here is theta. Now, if I take the opposite of angle theta, so the opposite of angle theta, so if I take the sine of angle theta, it's equal to the opposite, which is x, divided by the hypotenuse, which is d. So how much is x? It's equal d sine of angle theta. So the path difference, what they call it delta, is twice this amount because it comes d sine theta from here, d sine theta from here. So 2d sine theta is the path difference between wave 2 and wave 1. If these two waves interfere constructively, that is, if delta is equal n lambda, where n is an integer, this gives directly the Bragg's law, 2d sine theta equal n lambda. Okay, so the outgoing rays experience constructive interference if their path difference, that is delta or 2d sine theta, is a multiple of the beam's wavelength, n times lambda, where n is an integer. The angle theta is the angle between the incident beam and the atomic plane within the crystal. It is also known as Bragg's angle. Twice the Bragg's angle, or 2 theta, let's look here. Okay, so wave 1 comes here and it gets diffracted. Sorry, here is the reflection and here is the diffraction. So the diffraction angle is 2 theta. Okay, so twice the Bragg's angle, or 2 theta, is known as the diffraction angle. Just as a crystal has unique lattice vectors or direct space lattice vectors, which identify the unique crystal structure, there are reciprocal lattice vectors associated with every set of direct space lattice vectors. The reciprocal lattice vectors are vectors in the reciprocal space of the crystal. When an electron diffraction image of a crystal is made, a series of bright dots is seen as shown here. So if I bring a crystal and I shine electrons upon it and I see what happens at the detector, I will see something like this. I will see some bright dots and some black dots. Okay, the dots, the bright dots, are thought of as the reciprocal space version of the direct crystal lattice. So what I see on my detector is the reciprocal space. Okay, each dot is reciprocal lattice. Each dot is reciprocal space. In reciprocal space, is connected to each other by lattice. Each each dot in reciprocal space, in reciprocal lattice space, is connected to each other by a reciprocal lattice translation vector denoted by G. Just as in direct space, there is vector R that represents all the points in the direct primitive, in the direct lattice. Okay, vector R, we agreed that it is N1A1 plus N2A2 plus N3A3. For every R, there is a reciprocal lattice translation vector G given by V1B1 plus V2B2 plus V3B3, where V1, V1, and V3 are integers, and B1, B2, and B3 are reciprocal primitive lattice vectors described in lecture 7, and we will come across them again over here. Reciprocal space is sometimes described as Fourier space. Okay, so a crystal is invariant under any translation of the form of equation R equal N1A1 plus N2A2 plus N3A3. In mathematics, a Fourier series decomposes any periodic function of period t into the sum of a set of simple oscillating functions, namely sines and cosines, or equivalently complex exponentials. One can write the Fourier sum of, over here, the crystal is invariant under the translation of the form of R equal N1A1 plus N2A2 plus N3A3. This means that any other property of the crystal is also invariant under R. One example of that is the electron number density. You think of this as, if I take one point in space, how many atoms are there? Okay, or what is the electron density over there? Okay, we will call it N of R. It's a function which is periodic, okay, with R, with periods A1, A2, and A3 in the direction of the crystal axis. We have, so because it is periodic, we have, and it is invariant under translation, so N of R plus R, that is, if we translate vector R by vector R, we should go back to our function. Because we can write our function in this periodic form, then we can write it, we can write the Fourier sum of the electron density as summation over G for NGE to the I G dot R. This is how we represent the Fourier sum of a periodic function, okay? Whose Fourier components, NG is called the Fourier components. It is 1 over VC, the integral over the cell of N of R e to the minus IG dot R dV, where VC is the volume of a cell of the crystal. To proceed, we need to find this vector G such that N of R plus R equal N of R. Here, I say revisited because if we use vector G that I explained in lecture 7, which is V1, B1 plus V2, B2 plus V3, V3, where B1, B2, and B3 can be calculated from A1, A2, A3, the primitive lattice vectors of the direct lattice, such that Bi dot Aj equal 2 pi delta Ij, where delta Ij equal 1 if I equal to J, delta Ij equal to 0 if I different than J, then this condition is met. N of R plus R is equal to N of R. Okay, so let's do a simple exercise. Consider a plane HKL in a crystal lattice. Prove that the reciprocal lattice vector G, which is HB1 plus KB2 plus LB3, is perpendicular to this plane. Okay, so we have plane HKL. Okay, and we need to prove that vector G, which is HB1 plus KB2 plus LB3, is perpendicular to plane HKL. Okay, so to do that, choose points A, B, and C on the plane HKL such that point A is 1 over H, 0, 0. Point B, 1 over K, sorry. Point B is 0, 1 over K, 0. And point C is 0, 0, 1 over L. Remember how we make these HKL, right? So we have whatever points we have, we take the reciprocal to get HKL. So if you want to go back to the points, we take the reciprocal as well. Now, vector AB, so this is vector AB, it's equal to 0 minus 1 over h, so minus 1 over h, 1 over k minus 0, so 1 over k, 0. Take two vectors, it's enough. And vector AC is 0 minus 1 over h, so minus 1 over h, 0 minus 0 is 0, and 1 over L minus 0 is 0. So these are vectors. Now, I need to take AB dot G. If I can prove it to be 0, it means G is, or G dot AB, it's the same thing. If I can prove it's 0, implies AB and G are perpendicular. Then I take G and AC. If G is perpendicular to AC, if G dot AC is 0, implies G is perpendicular to AC. If it's perpendicular to AB and to AC, it means G and ABC are perpendicular. So how much is this? G dot AB. So we start. So it is HB1 plus KB2 plus LB3 dot AB, which is minus 1 over HA1 plus 1 over KA2. That's it. Okay, now let's do the dot product carefully. This is here vector, vector, vector B1, vector B2, vector B3, vector A1, vector A. Okay, now I have here HB1 dot minus 1 over HA1. Here you have to remember that AI dot BJ is equal to delta IJ. That is the only things that survive if I and J, this is equal to pi. If I equal to J and it is equal to 0, if I different than J. Okay, so the only terms that live is HB1 dot minus 1 over HA1. This term will survive over here. The other term will die, and then B2 dot A1 is 0, B2 dot A2 will survive. So these two will survive. This will give me HB1 dot minus 1 over HA1. This is H over H is 1 minus, so it is minus 2 pi. Okay, B1 dot A1 is 2 pi. Okay, and the other term will give me KB2 plus 1 over KA2. So this will give me plus 2 pi. And this is equal to 0. So I proved that G dot AB is equal to 0. Similarly, one can show that G dot AC equal to 0. Okay, so similarly, you can do it on your own. You can prove that G dot AC is equal to 0. Here, if not, just shoot me an email and then we can go through this again together in the live session. Now, prove that the distance between two adjacent parallel planes of the lattice is DHKL equal to pi over G. For this, I will look at the drawing. So we choose two adjacent planes. So we need to prove that the distance between these two adjacent planes, one of them is this ABC, okay? And another plane, I haven't drawn it here because I don't want to cause mess, but it is something that passes through O. Okay, so let's take another plane over here, perpendicular, parallel to it. Just imagine, okay, that there is another plane over here parallel to it. Okay, but we will take it passing through O. So we choose two adjacent planes, including one that passes through the origin O. Let n be a normal unit vector parallel to G. What does it mean? N is a normal unit vector parallel to G. This means that n in absolute value, so absolute value of n is equal to 1. Okay, this means the absolute value of n is equal to 1. And this also means that n vector is equal to vector G divided by G. So this, in order to get the absolute value, is equal to 1. Okay, because if I get here the absolute value of a G and divided by G, which is the absolute value of G, I will get 1, and it is parallel to it, so it is parallel to it. Okay, so let n be a normal unit vector parallel to G, so as absolute value of n is equal to 1. I have OA dot n. Okay, so this is vector n, which is a unit vector parallel to G. Remember that G is perpendicular to this ABC. So OA dot n is equal to what? It is equal to OA times the absolute value of n, which is 1, times cosine angle alpha, which is the angle between OA and n. Okay? But cosine alpha, now if you look at this triangle OHA, so if you look at triangle OHA, perpendicular or right at H, okay? If you look at triangle OHA, right at H, what is cosine angle alpha? It is O cosine angle alpha, it is OH, right? It is OH, cosine of the angle alpha is OH divided by the hypotenuse, which is OA. So cosine alpha is OH over OA. So you come back here, OA dot n is OA times 1 times cosine alpha. This is definition of dot product. OA times n times cosine alpha, and the absolute value of n is 1, okay? But OH is equal to OH, this distance. It is actually the distance between the two planes, because there are two successive planes, one passing through O and one coming right after that. It is equal to OA cosine alpha. So we get from these two equations that OA dot n is equal to the distance between the two successive planes. So OA dot n is DHKL. Now, I know that n is a G over G. So OA dot n is OA dot G over G. But OA dot G is what? OA, I have 2 points here. I have point O, which is 0, 0, 0, and A, which is A1 over H in the direction of vector A1, right? So it is A1 over H. Dot vector G, which is HB1 plus KB2 plus LB3, or this is how they named it. So it's HB1 plus KB2 plus LB3. Now, if I take the dot product of these, the only term that will succeed, that will stay, is A1 over H multiplied by HB1. The other two will die because A1 dot B2 is 0, A1 dot B3 is 0. So I'll be left with A1 over H times HB1, which is 2 pi. So OA dot N is equal to 2 pi over G. Why? Because OA dot G is 2 pi. So I got this here. OA dot G is 2 pi. So OA dot N is 2 pi divided by G. But OA dot N is the distance between the two successive planes, implies, if I compare 1 and 2, I get the distance between two successive planes or two adjacent planes to be 2 pi over g. Okay. The last part, prove that for a simple cubic lattice, this distance is a over square root of h square plus k square plus l square. Here, for a simple cubic lattice with a lattice constant a, the reciprocal lattice is also a simple cubic lattice with lattice constant 2 pi over a. Remember, when we calculated B1, B2, and B3, we found that B1, B2, and B3 in absolute value is 2 pi over a. So the distance is 2 pi over g. G is nothing but the square root of, in order to get g, I get this vector HB1 plus KB2 plus LB3, and I get its absolute value. So if I get first the square of that, that's H square B1 square plus K square B2 square plus L square B3 square. But I know that B1, B2, and B3 are 2 pi over A, so I get 4 pi square over A square outside into H square plus K square plus L square. Okay, now G is 2 pi over A square root of H square plus K square plus L square, implies this distance, which is 2 pi over G. So it is 2 pi over A square root of H square plus K square plus L square. The A jumps up, and the distance between two successive planes become A over square root of H square plus K square plus L square. This is a very important identity. Okay, so by now you should know that you should know by now that the reciprocal lattice vector G is perpendicular to the plane whose indices are H, K, L, okay? And the distance between two adjacent parallel planes of the lattice is DHKL equal 2 pi over G, okay? That's the distance between two adjacent parallel planes. And for a simple cubic lattice, this distance is A divided by square root of H square plus K square plus L square. That's it for today's lecture. Bye-bye.